Alright, so I'm redoing a handful of videos in section 2.3. I think I got overly theoretical, and section 2.3 was probably the worst video of the ones that I'm redoing this summer. I wrote the section with the idea of introducing some theory, and the theory really doesn't have a lot to do with how we generally solve the problems. It has to do with how you find derivatives, applying a rule technically as opposed to maybe how it's actually used in practice. So the first 10 problems are just here to introduce the theory on how to use something called the chain rule. And if my boss read this, he'd probably vomit. But basically, the chain rule is a rule that allows us to find a derivative in a problem that has a parentheses with an exponent outside of it. And the theory behind the rule is kind of complex, but the rule itself isn't particularly hard to apply. So I'll try to, before I jump into doing some problems, just explain what the chain rule is and how how the chain rule works without really formally maybe defining the chain rule. So I'll make up a generic problem. This problem is not from the handout, so this is just a made up not from the handout or from my web page, just to illustrate the chain rule. So if I give you a function that has a parentheses with an exponent, and I wanted to find the derivative. So this is a perfect candidate for a chain rule derivative. Anytime I have a parentheses that has an exponent, whether there's a number written in front of the parentheses or not, this is a candidate for a chain rule. So this would be a candidate for a chain rule. Let me show you how to do the derivative. The derivative is super easy. It's real similar to the general power rule. To use the chain rule, you multiply the exponent by the coefficient. We've done that a bunch of times already. Multiply the exponent by the coefficient, or the number in front of the parentheses. Lower the exponent by 1, and we've done this a bunch of times too. So that's the start of the chain rule. There's an extra step that students forget a lot. So this part of the chain rule is no different. I'll write down what the derivative is. I'm going to take the exponent 4, multiply it by the coefficient. I'm not going to change the contents of the parentheses. I didn't write that down, but I'm not going to. So this is, I'll call that, I don't know, half or 2/3 of the chain rule. To finish up the chain rule, after I multiply the exponent by the coefficient, the exponent being the 4, the coefficient, the number in front of the parentheses, 6, lowering the exponent by 1, and then multiply by the derivative of what is inside the parentheses. So there's just this extra step. If you have a parentheses with an exponent, multiplying the exponent by the coefficient we've done a bunch of times, lowering the exponent by 1 we've done a bunch of times, but we have the extra step here to multiply by the derivative of what's inside the parentheses. And notice how when I multiplied the 4 by 6 and rewrote the parentheses down with the exponent lowered, I left myself some space. In this space is where I usually add the multiply by the derivative of what's inside the parentheses. I could have added it after the exponent, but I usually put it right here. So I'm going to add multiply by the derivative of what's inside the parentheses. The first term inside the parentheses is an x squared. It has the derivative of 2x. I just bring the 2 out front, lower the exponent by 1. The second term inside the parentheses, the first power term. First power terms have a derivative of just the number in front of the letter, so the derivative of 9x is just 9. And the derivative of the minus 7, because it doesn't have a letter, has a derivative of 0. Oh, I wrote off the screen here. So I'll just multiply this 4 by 6, because that's multiplication that probably should be done. I probably wouldn't multiply that 24 in through the parentheses that it's next to, because that would produce something here that would have a common factor of 24. I never clear the exponent or change the piece that has the exponent unless there's a common factor. So the derivative of f of x equals 6 times the quantity x squared plus 9x minus 7 to the 4th power is just 24 times 2x plus 9 times x squared plus 9x minus 7 to the 3rd power. So that's the chain rule. There isn't anything else in this section other than that, other than we're going to have to be able to use maybe the chain rule and the product rule that we learned in the last section together. We might get some problems that have fraction exponents or have radicals and I turn them into problems with fraction exponents. So I'm skipping all the way between 1 and 10, and I'm just going to start going into the problems between 11 and 20, and I'm going to completely ignore my instructions. I guess we can skip 11 through 20 too. How beautiful. 11 through 20 are also more problems that, if I was teaching how to use the chain rule, how to find the derivatives of parentheses that have exponents outside of them, this is more theory that we can bypass. How beautiful is this? And it's not going to impact us in the least. So skipping all the way from 1 to 20, moving on to problems 21 through 32, I'm going to use the chain rule to find each of the derivatives. In this hint, which is so complex, would be applicable if I was teaching you the kind of long, non-shortcut way to find a derivative of a parentheses with an exponent. There are other times where I'm going to do a derivative with like e's and ln's, natural logs, that I'm kind of technically using a version of the chain rule, but I won't get into that. That's too complicated right now. So let me just do some of these derivatives. So parentheses with an exponent, simple to find a derivative. I simply just write the derivative symbol, multiply the exponent by the coefficient. In this problem, since there isn't a number written to the left of a parentheses, there's an implied 1 written to the left of the parentheses. So on the first step, where I multiply the exponent by the coefficient, I'm multiplying the exponent of 2 by the 1 that's implied in front of the parentheses, which will give me a 2. I could have really just brought the 2 out front. I usually leave myself some room. I leave the parentheses unchanged. I lower the exponent by 1, so exponent times the coefficient, lower the exponent by 1, just a generic derivative that we've done a bunch of times. The next step is to multiply by the derivative of what's inside the parentheses. If the derivative has 2 terms in the derivative, then I probably write a parentheses here. Here the derivative is just going to be a single number. I really don't need a parentheses, but it's never wrong to right to the left of the parentheses, put a parentheses when you're using the chain rule, and then do the derivative of each term inside that parentheses and shove it in this parentheses. Here, the derivative of 5x, since it's a first power term, is just the number in front of the x, which is 5. The derivative of the minus 3, because it doesn't have a letter, has a derivative of 0. So the derivative for number 22 is going to be 10 times 5x minus 3 to the first. I'm going to multiply this 2 and the 5. Don't need to write the exponent of 1. This I would call the best answer because it's completely factored. If you wanted to, you could clear the parentheses and make it non-factored by multiplying 10 times 5x and getting 50x, and 10 times minus 3 and getting minus 30. This is, I would call, an okay answer. But it's not as good as the best answer because it's not factored, and this has a common factor of 10 that you could factor out. So your problem 21 should work exactly the same way. I'll move on to my next sheet. So for problem 24, I'll just do a crack at it. You might pause the video and do problem 23. So parentheses with an exponent is a perfect category for a chain rule. I multiply, to do the derivative, I multiply the exponent by the coefficient, leave myself some room, leave the parentheses unchanged, lower the exponent by 1, and where I have that room, I'm going to take the derivative of each term inside the original parentheses. The derivative of 8x, because it's a first power term, is just the 8 that's in front of the x. The derivative of the 7, because it's a constant, has a derivative of 0. And then the numbers to the left of the parentheses, the 5 times 3 times 8, I'd probably multiply those out and get 120. And so for problem 24, I'd say the best derivative is 120 times 8x plus 7 to the 4th. There isn't really anything I can do to simplify that. Technically wouldn't even be correct to multiply the 8 and the 7 by 120 because that would be doing multiplication before exponents, and that's violating the orders of operations. Alright, keep mushing on. So the problems are getting a little bit uglier here. Usually in math we don't want to see negative exponents in answers, but if the original problem has a negative exponent, there isn't any reason to make the negative exponent positive. But when I do the derivative for problem 26, maybe I'll write the answer two ways, with a negative exponent and with the negative exponent turned positive. But if a problem has negative exponents to start, it's usually acceptable to leave the exponent negative. If the problem started with positive exponents and my algebra produced negative exponents, then I'd probably take the time to make the negative exponent positive. So for 26, simple derivative, so I'm going to write the derivative symbol. I'm going to take the exponent of negative 3, multiply it by the coefficient of 2, leave myself some room, and then I need to lower the exponent by 1. I need to go negative 3 minus 1. And on my calculator, when I say negative, it's the bottom negative, so down here by the decimal, so negative 3. When I say minus, it's by the plus sign, minus 1. Those have the same sign, so they're going to add together and stay negative. Negative 3 minus 1 is negative 4. So that's the exponent times the coefficient, lower the exponent by 1. To the left of the parentheses, I'm going to write the derivative of each term. I always can put a parentheses if the derivative, like in the example I showed, has a couple terms, then a parentheses is necessary. Here, the derivative is just going to be one number. I don't really need a parentheses, so I'm just going to put a times sign. So the derivative of each term inside the parentheses, the first term is a first power term. Its derivative is just the number in front of the x. The minus 6 doesn't have a letter. It has a derivative of 0. And so now I'm going to multiply the numbers. Negative 3 times 2 is negative 6 times 5. So negative 3 times 2 times 5 is negative 30. And then times 5x minus 6 to the negative 4th. This is probably how I'd leave my answer. So this will be my answer to this problem. Specifically, the original problem had a negative exponent. I don't mind my answer having a negative exponent, but probably a better answer, an answer that I would give if the original problem had a positive exponent and my derivative had a negative exponent, probably would be this. I'd probably form a fraction. I'd take the quantity that has a negative exponent, move it to the denominator of that fraction, and leave the coefficient up in the numerator. So that would be a shortcut trick that we learned in intermediate algebra that you might have forgotten, to make a negative exponent into a problem with a fraction. You have to be careful not to move coefficients when you're taking the quantity with a negative exponent and making its exponent positive. That'll probably come up pretty quickly here when we start getting to the fraction exponents, because fraction exponents often turn into negative. They start with positive exponents, but the derivatives have negative exponents. All right, so we'll just keep going, and then eventually it's going to get a little more complicated because we'll start introducing the product rule that you may have not wanted to see again. So for 28, I'm going to write the derivative. There's an implied 1 in front of the parentheses. I'm going to multiply the exponent 3 by that implied 1 and get a 3. I'm going to leave myself some space. I'm not going to change the contents of the parentheses. I'm going to lower the exponent, and then to the left of the parentheses, after the 3, I'm going to write the derivative of each term inside the parentheses. And here, this is where I'm going to need a parentheses, because I'm going to have 2 terms instead of just 1 from the derivative of the contents of the parentheses. The 3x squared, to do its derivative, I multiply the 2 by 3 and get 6, lower the exponent by 1 and get a 6x. The minus 5x has a derivative of minus 5, and the 2 has a derivative of 0. That I would call the best answer. I shouldn't multiply coefficients in through the parentheses, because that just produces a quantity that can be factored, and so this is what I would call as the best answer. I don't clear these exponents ever. We start using the product rule along with the chain rule, we'll start to have common factors. I might factor out one of these exponents to make it go away, but I'm not going to FOIL out anything. So, I'm debating on how technical I should get here. Square roots is the same as 1/2 power. So anytime I see a square root, that's the same as a 1/2 power. For instance, the second square root of 16 is 4, and 16 exponent 1/2 power. So square root of 16, I say square root is the same as 1/2 power. That would say the square root of 16 is the same as 16 to the 1/2 power. In order to use the chain rule, I need to, anytime I have a radical, change it to a fraction exponents. And very specifically, if we get square roots, we'll change them to 1/2 powers. Cube root is the same as a 1/3 power. For instance, if I did cube root of 27, I'll get 3. And if I did 27 exponent 1/3 power, I'll get a 3, because cube root is the same as 1/3 power. Similarly, 4th root, same as, horrible grammar, the 1/4 power. So if I did like, clear math, oops, I don't know if I could do this like that first. Yeah, so 4th root of, oh my gosh, 256 and 256 exponent 1/4 power, they're both equal to 4. So I need to, if a problem has a fraction exponent and I want to find its if a problem has a radical and I want to find its derivative, I need to change that problem into a problem with a fraction exponent. So if I was doing problem 30, I need to rewrite with a fraction exponent. And this is the kind of problem, these radical problems will often start with positive exponents when we rewrite them. And the derivative will turn into a negative exponent, and that negative exponent I'll turn back positive. And well, let me just go through these problems. And I might have to say a little bit more about just the theory of working with exponents that you might have forgotten from intermediate algebra. But for our 29, your 29 and my 30, I'm going to use the trick that anytime I have a radical, I could turn it into a problem with a fraction exponent. Now I have a problem with a parentheses and an exponent, so I could use the chain rule. I'm going to bring the exponent out front. Technically, I'm multiplying it by the implied 1 that's in front of the parentheses, and 1/2 times 1 is just 1/2. I'm going to leave myself some room, and I'm going to lower the exponent by 1. So I'm going to, for the exponent, I'm going to go 1/2 minus 1 and do math and enter twice. And that's going to be negative 1/2 for the new exponent. Normally, if I'm working by hand, when I lower the exponent by 1, I probably subtract by a fraction that's equivalent to 1 that has the denominator that I'm looking for. So if I was doing this 1/2 minus 1 without my calculator that doesn't care about common denominators, I would have done 1/2 minus 2/2 and gotten negative 1/2. The room that I left myself, I need to put the derivative of each term inside the parentheses. The derivative of x squared is 2x. I just bring the 2 out in front of the x, lower the exponent by 1. The derivative of 3 is 0. So now I can multiply that 1/2 and 2. And I think I can do that. 1 divided by 2 times 2 comes out to 1. They cancel each other. These 2's cancel each other. And then that's going to leave me with x times x squared plus 3 to the negative 1/2 power. So this is, not the best answer for 2 reasons. The original problem didn't have negative exponents, so probably my answer shouldn't have negative exponents. So I'm going to make the negative exponent positive. I'm not going to pull the coefficient into the denominator, but I'm going to create a fraction and move the term with the negative exponent down to the denominator. That's a good answer, but really the original problem didn't even have a fraction exponent. I should probably make the fraction exponent back into a radical, and this is the part at some point where I might have to spend some time talking about theory on how to take something with a fraction exponent and turn it into a radical that isn't just trivial. Here, this is a 1/2 power. It's the same as a square root, and when I introduce the square root sign, I don't need the parentheses anymore. When I get rid of the square root sign and create a fraction exponent, the contents of the radical need to be buried or contained in a parentheses. So this would be probably the best answer. So I used a bunch of tricks here. I took the square root, made it have a fraction exponent, used the chain rule to find my derivative. I had to multiply the 1/2 by 2 to simplify it. Needed to make the negative exponent positive by creating a fraction, and then best off, I made the 1/2 power into a square root. On a test, if you get this far and you don't simplify anymore or don't simplify correctly, that's like a -1 kind of mistake. So getting the bulk of the derivative correct and the simplification is, the simplification is less important than the derivative itself. All right, maybe I'll do 31 with you, just so you don't have to be stuck doing it. So for 31, Anytime I see a radical, I'm going to change it into something that has a fraction exponent. This is a cubed root. That 3 implies a cubed root. And anytime I'm asked to find a derivative of a radical, I create a fraction exponent. Now I have a parentheses with an exponent, and when I have a parentheses with an exponent, I do the derivative by taking the exponent. I'm going to multiply it by the coefficient. I'm going to leave myself some room, and I'm going to lower the exponent by 1. So technically, for the new exponent, I'm doing 1/3 minus 1. Again, my calculator rocks with fractions. If I just did 1 divided by 3 minus 1, it equals, and then math and enter twice, tells me the new exponent should be negative 2/3. If I didn't want to be bound to my calculator, then when I was subtracting 1, I probably would have subtracted 3/3, because 3/3 is a fraction version of 1 that has a 3 in the denominator, and 1/3 minus 3/3 is negative 2/3. If you're not good with fractions, then just use your calculator. I'm not done. That spot where I left myself some room, I need to take the derivative of each term inside the parentheses. The derivative of 5x is just 5. The derivative of 1 is 0. Didn't really need to put this derivative of 5x plus 1 in the parentheses because there's only one term and not two terms. Now I'm going to multiply 1/3 times 4 times 5. So I'm going to go 1/3 times 4 times 5. And math, enter, enter, gives me 20/3. And I know that if you're multiplying fractions by integers, you just multiply the numerator. So I just did 1 times 4 times 5 and then over 3. So this is going to be 20/3. And then 5x plus 1 to the negative 2/3. That's the derivative. It's simplified enough where if you didn't simplify further or made a mistake simplifying, it's just kind of a minus 1. But I'm going to make the negative exponent positive. I already have a denominator, so I don't need to create an extra level of the fraction. I just take the term with the negative exponent, move it down to the denominator, and now I have a derivative that has a positive exponent, which is better than one with a negative exponent. But now I need to make this probably into a radical, and this is tricky. So when you're going to make something with a fraction exponent that into a radical, this part goes under the radical, and the denominator becomes the index. It's going to be a cubed root. So if you have a fraction exponent, and it's not like 1/3 that turns into a cube root or 1/2 that turns into a square root, if it's a number other than 1 in the numerator, that number is going to get buried under the radical. So when I go to write this answer nicely, the 20/3 part is going to stick with me. Fraction exponents turn into radicals, and if the exponent is not 1 over something, only the denominator becomes the index, so that 3 is going to become the index, and the 5x plus 1 squared is going to go under the radical. And that I'd call the best answer. I mean, it's a bit overkill to go that far, but that, you know, if you were looking at a key, that's probably what the key would say. So I think I'm going to break this into a part 2, because in the next part, we start using multiple rules, and the problems are, I'll say messier, to be kind. So that's going to be the end of part 1, and we'll move on to section 2, 3, part 2 here in a second.